My talk will be about one part of my work, interaction in particular with scientific visualizations. So I will start first with explaining a few parts of that title, visualization, in particular scientific visualization. We are dealing in that domain with data that is different from the data that we heard about before. So our data does not necessarily come in tables or in form of graphs, connections, but we have data that has a specific meaning and placement in space, in 2D space, but more often in 3D space. Think about, for example, as here on the slide, about data that comes in the area of medicine, where we scan people's bodies, people's brains. We can measure activity in the brains, for example. We have data that we simulate, such as in fluid dynamics. If we build new airplanes, we want to know how they fly, what does the flow around the wings, how does that happen? Or in very small and molecular data, where we also have models that are where each element has a specific position in space. We may have other data about that, about our subjects, but we also have at least some data that is explicit in 3D space, and that's important for the work that we, the kinds of interactions that we want to accommodate with them. Now, the problem with this kind of visualization is that the data, as in all domains where we collect data, becomes more and more. So here on the slides are a couple of examples. In this Pan-STARRS project, for example, they capture 2.5 petabytes per year. In CERN, they capture 50 to 100 petabytes per year, and so on. So the data that we capture is enormous. In addition, it's not just enormous, it becomes bigger and bigger and bigger all the time. This is an example from genetics, the gene bank entries by date, and that goes up to 2008. And you see that the sequences that we collect in millions grows exponentially. The base pairs, in this case in billions, also grows exponentially. So we have to deal with all this data, and it's increasing this problem. Now, traditionally, we generate visualizations. That means we look at the data, we make it visible in nice images, in movies, and look at that. But that's not enough. That means I just can get an impression that somebody else wanted to show me. But to really understand the data, in order to work with it, I have to essentially explore it myself. So this is kind of the area that I'm working with. In particular, exploring data on large displays, and we heard a little bit about those before already. Let me give you an example. This is a visualization of some weather data in 2D, so that's something that we probably are all familiar with from the weather forecasts on TV every night. This is from a particular storm in Europe a couple years ago, where each of these little elements shows the direction of the wind and the speed of the wind. This is just a visualization that tells you, okay, there's a big wind, but I don't really can understand more about what's happening, why are things happening, what kind of patterns can I explore. So instead, if you provide an application so that people can explore this kind of data themselves, can create little elements to place on the screen where they want in order to probe data, in order to look at bigger storm elements or bigger wind patterns, then it can be a lot more intuitive for people, and people can learn a lot more about this data. Also, with these kinds of displays, we can allow several people to work together in teams in order to explore the data. How does that work? Well, well, we heard that in the future we'll buy that in form of tablecloth that we can put on tables. That will be probably a few, let's say, decades off. What is right is that certainly this technology is becoming cheaper and cheaper, and in particular, these are two technologies. One that is very common today on the left side use some kind of frame that you can put over any kind of existing display that you can use with projections. This is kind of the technology that we use now. Technology that's just coming up is where the touch sensing essentially is built into your display. I'm very confident that in a couple years, maybe 2 years, we will be able to buy TV-like displays that have touch built in. So we can get the touch information quite readily. The specific technology in this project that we used here is also a frame technology where a frame is placed on top of a display. And this frame has cameras in the 4 corners. And along the sides are strips of infrared LEDs. And then these cameras essentially see a shadow of a touching hand or touching pen or touching finger that comes close to the display. And then by triangulation, we can figure out where are the touches and how big are the touches. For this specific visualization project, we make use of, in particular, also this sensing of the size of the touch. That means we can distinguish, on average, that a pen is touching the display, that a finger is touching the display, that we have 2 fingers touching the display, or that a fist or a full hand is touching the display. With that, with those kind of tools that we have built in to our bodies, essentially, we can now then draw little elements that we can use to explore the data. These are called glyphs, and here I have drawn an arrow, for example, very common glyph, and I can create all kinds of different glyphs. And now, what happens is I have data elements. I have the data, that's kind of this kind of strange color image in the top that encodes the speed and direction of the wind, and then I have additional layers that help me to explore the data, other aspects of the data, such as a map, the wind speed, maybe the pressure, air pressure of the existing, of that space. And now I basically layer them on top of each other and can start placing those kind of exploration elements, those kind of glyphs onto this stack of data. And then what happens is that this glyph looks into the data, figures out at the correct location what is the current direction of wind and what is the current speed of the wind, and then it turns itself accordingly and resizes itself accordingly. And if I place a different glyph somewhere else, that looks at a different location in space, gets a different orientation, gets a different speed. Okay, so that's the principle behind this. How does it work? Well, we can start by drawing these glyphs, and you see that the bigger element I use to draw, the bigger also the drawing happens, so that is very intuitive. And if I'm not happy, then I can delete it again, draw something else, and put the pen down again to start exploring. And if I just use one finger, then only glyphs are being placed. It's a very easy way of exploring this data and also illustrating interesting parts. And then again, if I'm not happy, get rid of them, start over. Or a different glyph. And then with the fist, which is the more expressive gesture, I can place more. And then I can already see some streams where some important flows in this data. Then I get rid of them again if I'm not, or if I want to do something else. I draw another one, even smaller one, and this time I use 2 fingers, and this places little sources onto the data set, and that emit these little glyphs, and they follow the data flow in this data set. And then I can explore what's happened using dynamic matters. And I can draw a different glyph and place a source that places those different glyphs. I can also put them into little color pots and then can start exploring this. And here you see a little close-up of what has happened, and I can see that this top swirl is kind of isolated and nothing really happens. All right, I'll stop here. It's just the video goes on to show a different data set. So what I showed you so far is relatively easy. It's easy because I have a touch surface which is in 2D. So I touch on a 2D location, and I have data that is essentially 2D. Now, I told you at the beginning that scientific visualization typically deals with 3D data. And that becomes then more important, more difficult. But before I get to that, a little bit about collaboration as well. I mentioned that these displays, these large displays, allow collaboration between people. And we looked at what happens if you let two people interact with this 2D data set. And it's interesting that even though we made the application only single touch, there was a very interesting dynamic happening between the two people. So there were, for example, times when they were just looking at the data, going back to get an overview. But then somebody had an idea and explained that to the other person, and then the other person would come in and also add his ideas in that case. And sometimes it even happened that they were almost racing each other to the screen in order to be the first to present their ideas. The nice thing about this is also compared to, say, a traditional mouse-based setting, that you can point and gesture. So here, you see this low-pressure system there, the dark spot, and he points that out to his colleague and tries to explain something about that. And then the other guy shows what the wind pattern basically does based on this observation. But now about this 2D versus 3D problem. So I said 2D is easy because we have a 2D touch surface and 2D data. But now what happens if we have 3D data? So here you see that I still touch in 2D. I can't really touch through the display because only the display is sensing where I'm touching. But I still have data that is in 3D, and I need to manipulate that. And that's a problem that's not easy to solve. And there are a lot of, number of possibilities, and let me show you a selection of those. So this is from a project where touch interaction was used not necessarily for visualization, but more for psychology sessions. But that illustrates very nicely how you can interact with 3D objects. This is a table display, and if you touch just with one finger, you can move the objects in space. Now, if you use two fingers, you can start rotating them, and you know that from your iPhone. But here, we also have the third dimension. We want to be able to lift objects, so if we move the fingers apart, the objects kind of come up. And there's a physics simulation behind it, so the objects also jump around in space. So essentially, we also need to rotate things around all the three axes in space, and that's happening if you use a third finger. So you start with two fingers, define an axis, and then you can start the rotation. That allows you to control 6 independent parameters, but the one that is missing is also size. You want to be able to resize things as well. And this is where we have a different metaphor for that. It's a drawer where you can place things in and then you can resize them. And the important thing is that you always, depending on the different applications, you have to figure out what are the most important interactions, and these have to be more accessible. So if you have an iPhone and you want to look at photos, then resizing is more important. If you have 3D elements in this kind of sandbox situation, then you want to probably lift them rather than resize them more often. And then there are more metaphors to affect other properties of the space, such as making parts of that water. And the application for this was a type of psychology called sand-trace therapy, where psychologists work in particular with kids to analyze what kind of problems they have. And typically they do that with sandboxes and a lot of figurines, and then the kids act out what they talk about. But a certain type of kids, when they come into puberty, that's no longer cool. But the hope is that working with a table like this, that's more cool, and then you can start creating those kind of scenes. And here, it's a scene with two dinosaurs, and we'll act out the different things right now. So there's a really peaceful plant eater, but then there comes a big guy, and yeah. Okay, so this is one way of dealing with the problem of mapping this 2D touch to 3D. Notice that the objects here are fairly big, so that's interesting. What happens, however, if we still have big objects, but there is also a data layer on that object? In this case, we have several planes that carry data themselves. And now we want to be able to interact with that. But now we have to be able to interact not only with the objects, but also with the data, and sometimes even with several hands. So the way we solve this is we take inspiration from our traditional interfaces, where we have a mouse. Now, on the touch display, we don't have a mouse, but in this case, we used a virtual mice. So here we have these planes, so we can switch to a 2D view, but then we also want to see them in 3D in order to see relations between them. And these little magnifying glasses in the top, those are virtual mice, and there's one per information plane, one per visualization plane. And with these virtual mice, we can now solve the problem that we want to be able to interact with the objects that carry the information, also interact with the information itself. So with the mice, and I think this is being shown in just a second. So here, first the interaction with the planes themselves, and then I can start seeing relations between the different visualizations. And then I can start using the mouse and find detailed information. The mouse, this virtual mouse, also solves another problem that we have in scientific visualization or generally touch interaction, that we need precision. We need to be able to locate things very precisely. And this mouse kind of zooms in and gives us an undistorted view of the object, and we can very precisely place our interaction point and explore this data. Okay. Now, so far we had objects that we wanted to interact with that had a certain size. But what happens if I have data that essentially does not have a size? And this is an example of such data that does not have a size. So here I have a simulation of two galaxies colliding, and each data element is essentially a point in space. And as we know, points do not have a size. So how do I interact with these particles? And here the idea is that let's not interact with the individual particles, but let's interact with the space they live in. But on the other hand, I don't want to see that space as just a box, because I'm not sure that my data will always be nicely centered in that box, and I always will have the right, right data that I want to explore in the center. So the idea is, let's use as an interface element the frame or border around my data. And that comes from how we interact with objects in a piece of paper as well. So if I have a piece of paper and touch it on the side and move it up and down, then that paper kind of starts to rotate. If I touch it on the side and move it perpendicular to the side, then it starts to move in X and Y. And that's kind of the interaction that we are shooting for with this one. Let me show you that in a video. So here we have this frame that we use, and we start by just zooming. So these corners are for zooming in and out. And then in the center, just as you would expect, I start moving objects, moving the space. And then if I start at the frame and move perpendicular, that starts a rotation. So I can freely rotate this, but it's also important to constrain it. So if I touch another frame, then I can start this rotation around just one axis. And the frame that I touch determines basically which axis it's being constrained to. And then if I touch also on the frame, but this time move along the frame, that kind of rotates the whole thing. And I can start at any frame, doesn't matter. All frames behave the same way. And then I have this last axis of translation, that's the Z translation, because it's a three-dimensional data set, so I can zoom in and out. Of course, people expect two-handed pinching interaction. That works in this case as well. Now let's see how we can explore a data set with that. So this is a different data set, cosmological mass simulation, which is very complex. Basically, the galaxies around our neighborhood from the beginning of time after the Big Bang up to now, and then the astronomers want to find out, does it look any similar to what we see today? So what can we learn about this evolution? And here we start looking at a specific type of the data set. This is not the center, but I still expect that when I rotate the stuff that the object that I see in the center, that's kind of the center of rotation. And then I go into a different, or she goes into a different location. And again, the same thing happens. So even though I interact with the space of the data set, it still has to take into account which part of the data is being shown at that time. So here again, rotation happens intuitively. Now, that works for one type of data. We showed that. But does it work for other data as well? And for that purpose, we looked at a completely different branch of science, neurology. And here we want to explore what does do the connectivity or the connections, the brain fibers in a human brain look like, and how does that relate to the brain and the skull. And here the interesting thing is that this data is different in the sense that it doesn't have a center. So brain kind of has intuitively a center. So this time we switch two interactions around. This time if you start in the center, you will start rotating because the rotation is more important this time than the translation. And if you start at the frame and move perpendicular to the frame, then that will be a translation. So here, oops, sorry, once more. There we go. Again, the corners are for zooming. Translation from the frame if you move perpendicular to the frame, and rotation in the center. And the rotation on the z-axis, again, along that frame. Now, another important interaction here is that we want to be able to move these cutting planes, right? And so here we use this two-handed technique with the frame being touched. And when you start putting your finger in the center, you see a little cross of the coordinate axes. And the one that you move along, that's the one that is being selected for moving the cutting planes. And then another important interaction is that you want to be able to select the fibers that you see at a certain point, and this happens if you touch with two fingers. So that kind of technique also works for different branches of science. Currently, we're looking at even more complex interactions. So typically, you don't only have like whatever 6 or so parameters that you need to affect. So not only the position, orientation, and size of the data set, but we want to explore more. In scientific data sets, this is an example from fluid dynamics, fluid simulation. You often have the case that you want to be able to move cutting planes to that. So you want to be able to move these cutting planes. You often also want to be able to place particles into the data set at locations. Again, you have only a 2D surface that you interact with, but you want to be able to place these particles, the seed points, in 3D space. And in this case, what we do is we use the cutting planes that you see on the left, and we place a 2D version of what this cutting plane intersects on the right. And then if you place your finger there, then that puts a seed point into the data set, and you see that from that seed points on the left, a little flow line is being created that shows you the evolution in the data set. We're also looking at settings. How do you have to set up such an interactive surface in order to explore scientific data effectively? Does it have to be always vertical, like the examples that I showed mostly, but maybe also we want to have it in a drafting table form, or sometimes also on a table. So we're currently working on having such a reconfigurable display and looking at how scientific visualization can be supported by that. Scientific visualization often traditionally is also being shown and looked at in stereoscopic projections. That means you have glasses, essentially your 3D that you can buy nowadays, just a little bit larger. The problem with that is when you can't really touch these virtual objects that kind of hang somewhere in space anymore. The idea is, can you have a touch surface that gives you feedback and then interact with that stereoscopically projected 3D object in front of you. And that brings me to the end of my presentation. And before we have questions, I believe Etienne is going to go on and talk a little bit about this Digiscope project that is running here.